Simulink just gives you the feel of that block diagram. It's graphical. That's all. But otherwise, you can always code as well. Okay. So it's not necessary to use Simulink for everything. But so you go to the library browser. Yeah. Once you go to this library browser, search for the things. Okay. You want to have a step input. So you can search for that. So this is a step input. Okay. Take this, drop it here. Okay, that's the step there. Then what else you need? Tell me what are the things that you need? What are the things that you need? You need a scope. Why no one is responding? This is a scope. So that's a scope. And then what else do you need? Yes. Can somebody respond, please? Hello.
Yes, sir.
Yeah. What else do you need? Step input I've taken, scope I've taken, then
Controller.
controller we'll see later. Sum, okay, the comparator. Okay, so this is the comparator. Take this. Then what else do you need? You need what is that? Tell me, what do you need? You need a transfer function, right?
Yes, sir.
So this is a transfer function. Take this. What else do you need? So this is a step input. You have this thing here, the comparator, and then you have the transfer function, and then you have the scope, and then what else do you need?
Step output units.
Step input is there, no? I've already taken. You need a gain. You need a gain. Okay. Take this. Take this gain. Okay. Okay. Let's start connecting. So connect the scope to the comparator. Comparator to the transfer function to the scope, and then this one should be in the reverse direction. So right click and rotate, flip block. Okay, it flips the block this side. Okay, and then what you do, you have this connected to this, and then this thing you connect to this, and then you need to have a negative feedback control. So you click on this and then change this thing to negative. Okay, so now what do you need to add? You need to add another gain, okay, for the controller. So open this gain, you add one more gain. So you put that gain here. So what have we added? What is this called? What is this called? No response.
GCFS,
Yes,
sir.
sir.
Okay, controller. Okay, then if you want to have a PID controller, what else do you need?
We need to have gain, sir.
Integral gain and
Hmm.
We need to have
differentiator.
gain.
Okay, integral 1 by s is the integrator. Take that. Okay, now how do you connect this? So make some space here. Okay, so where do you put this 1 by s? 1 by s, and then you need a gain. Okay, copy this. So do a control C, control V thing. So have it here, and then you need a derivative. Okay, so go to the library browser again, type derivative. You get this, take this. Okay, so for this you need a gain. Copy this, paste it. Okay, now what do you do? So connect all these things. So connect this. Connect the derivative. And then connect this thing. Connect this. And then what else do you need to do? Hmm? What do you need to do now?
We need to connect the integral gain and derivative.
Yeah. So for that, what do you use? You use a sum, right? So let me make some space here. Now you need to have a sum here. So copy this thing and then paste it here, and then you need to edit this. You want all to be plus, so remove this minus and then put another plus. Say okay. You'll have 3 plus. So you bring this here, you delete this thing, and then connect this to this one to this one to this one, and then connect this to the transfer function. So this makes the PID controller. Any doubts in doing this?
No, sir, no doubts.
Okay. So what you have to make sure is here it should be a negative here. Okay, because you're comparing the error with the desired output. Okay, so this must be a negative, minus, and these three things should be positive. Okay, these three should get summed up, so all three are positive. This one is negative over here, so this you should take care. And then this is kp, ki, and kd values you need to give. Okay, that is PID tuning. So any questions? Try. Is the library browser loading for you?
We will try something.
Yeah, try that now.
Taking so much of time.
Yeah. Try, see if it's working. If it is not at all working, then focus on the root locus, control system designer, those things. Do what is possible now.
Sir,
Do whatever is working.
sir, can you show it again, sir?
Which one?
It's on the assembly link.
Again now.
Sir.
Which part? Which part you didn't understand?
After the scope, sir.
After the scope. You want me to explain or build again?
Build again, sir.
Build again. Okay. Can I have these things, or I should delete everything? Can I have the...
Delete everything and connect, sir.
Huh? I didn't get you. What?
Sir, delete everything and connect 1 second, sir.
Okay, delete everything. Fine. Okay, deleted everything. Go to the library browser. The library browser is over here. Okay. Go to the library browser. The first thing is the input. You need to give the input, right? Go for the step input. Okay. So step is over here. Bring that into this. Okay. Step will come. And then we need a transfer function. So type transfer in the search. The first thing what you get, you put that here. Okay. Have the transfer function. And then we need a scope. So scope, have this here. Okay. And then we need a comparator. So search as sum, SUM. Take that. So put the comparator over here, not connected. Okay. And then you need a negative feedback, unity feedback. So take the gain. Okay. You take this gain and keep it here. You want it in the opposite direction. So right click and say rotate and flip, and here flip block. So it flips this block in the opposite direction, and then you start connecting these things. So this to be given to this to the transfer function, this to the scope, and the output is to be taken from here. If you get that red color, it's not connected. You should get this black color. Okay, and then connect this to the comparator and make sure this, double click on this comparator and make sure this is plus and minus. Okay, negative feedback system. Okay, and then what you do, you move all these things a bit. So you can add another gain. Okay, add another gain to this, connect this like this. If you just bring it to that place, it will get connected. And then you need to have PID controller if you want. Yeah, this is only KP. Okay, this is only KP. If you want IND, integral and derivative, you go to the library browser, type integral, search for it, you get an integrator, bring that. Okay, keep that here, and then you need the gain for that, KI, you need to enter. So copy this thing and paste it here. So connect this, okay, and then connect this over here, okay, and then you need to have a derivative. So go to the library browser and search for derivative. So you get this derivative block, bring that, so keep that here. You need a gain for this, copy this again and paste it. You get the gain for the derivative, connect this over here and then connect this here. So these three things you need to sum up. So you can have this copy and paste it here, Control V, and then click on this. And then you need to remove that minus sign and have one more plus. You need to add three things. So apply that and then bring that here. Delete this link. Connect this to this one, this to the second one, this to the third one, and connect this to this. So this becomes the PID controller. And then you can go to this and say what is the final value that is required. You usually do it with 1, okay. And then you can double click on this. You can edit your transfer function. You can give the coefficients for the numerator, coefficients for the denominator. It will make the transfer function. And then you can look at the scope for the output. You can vary the KP, KI and KD values here. Any questions? Sanjay, you got this?
Yes, sir.
Okay. Any questions on this? Any doubts in control engineering so far, whatever is done?
Okay.
Okay. So next we'll see the control system design now. Okay. I think I have done the pole zero map and the R locus. Okay. So here there is a control system designer. The command is control system designer. So S is capital here, D is capital. So you get that when you type this. Okay. When you type control system designer, You get this. You just run this. See, have the Simulink also open. Okay, so it says case sensitive. So S is caps here, D is caps, and then run this. So you will see many things here. So close the Bode plot. We haven't discussed Bode. So close this and make this little bigger so that you see the root locus plot and the step response thing. Okay. So here you see the step response. If you see, so this is around 0.15. Okay. So we need 1 as the output. So what do? You change this gain. Okay. So you change this gain. In this direction. Okay. So when you bring it in this direction, it increases. Pull this some more. Okay. So you're getting some 0.82 or something. Okay. So you're increasing that further. So this is some 0.9 or something. This is 0.8. This is 1. So somewhere 0.9 something. Okay. So what are you doing here? What are you editing? Editing the. What are you editing here? What is this value?
Gain value, sir.
Yeah, the
Gain
KP.
value.
KP. Okay, this is KP. If you don't add a pole or 0, if you simply move these roots, okay, you are increasing the gain. So what you're doing is you're getting the gain for this. Okay, 55.748 is a KP. Okay, so we can have a P controller or a PI controller or a PID controller. So here the disadvantage with the P controller is you don't get the value of 1 exactly. So what is that called as? So whatever you do, you don't reach exactly that 1. Okay, there will always be some error. It may be very close, but that error will be there a bit at least. Okay, it will not be exactly 1. But look at the overshoot you're getting because of increasing this KP. Okay, so it's more than 1.7 or something. Okay, so this is not good because the overshoot is very high. So when you try to decrease this thing, your steady state error will increase. Okay, so this will come down now. So it has come down again to 0.9 or something. Yeah, any questions? Roshan?
But after some time, we will get the output one no, sir. After some 2 seconds, 1.5. If we decrease the KP value.
Just a second. If I have this dotted line, is it visible?
Yeah, sir.
So it is 0.8 something. Okay. So if I bring it here, it's going down. Okay. So if I increase this value, it doesn't go to 1 actually. It's not exactly 1. Here still there will be some difference, 0.99 something. Okay, but the point I'm trying to tell you is to reduce the steady state error, you are increasing the overshoot to nearly 2. Okay, which is not good. Is it correct? Do you
Yes, sir.
agree? Do you agree to this? You are
Yes, sir.
increasing the overshoot very much. Okay, so overshoot too much is bad. Okay, so that is why we say it doesn't, there will always be some steady state error with only the KP thing. Okay, maybe a little bit of overshoot is okay, maybe this is okay, but look at the value that you're getting some 0.85 something. Okay, 0.88 or something, close to 0.9 maybe. Okay, so for this overshoot you're getting some 0.9. You needed 1, but you're getting 0.9 with the KP, the P controller. If you edit the compensator, you get that value. What is that value? Okay. Any questions?
No, sir.
This is trial and error method, no, sir. This is and again.
The P controller. This is not trial and error. This is you are looking at the graph and doing it. Okay.
Yeah.
Trial and error means without looking at anything you do it is trial and error. Here you are looking at a graph and you are editing the graph. Okay.
Okay.
If you blindly go to this Simulink and enter some value over here without looking at any plot, that is called as trial and error. But when you are doing with the control system designer, you have a root locus plot here and you are varying the gain value, looking at the step response. We don't call this as trial and error. We call this as optimizing the value.
Okay.
Is any questions? You know how to get a PI controller, PID controller. Try those things. If you have any doubts, you can ask me. Okay. So here, if you see, this is the transfer function for this is 1 divided by s square plus 5s plus 6. 1 divided by s square plus 5s plus 6. Okay. So for this, for any value of k, will the system become unstable? Look at the root locus editor. Will it become unstable? Will the system become unstable if you keep changing the value of k? Unstable
Yes,
region
sir.
is over here, okay, after this 0 on the right side. This thing is moving only in the vertical direction, okay. The pole is moving in the vertical direction, it's not moving in the horizontal direction, okay. So this will not become unstable, the system will not become unstable, but you just have to you don't have the unstable thing here, but you just have to optimize the p controller value, that's all. Any doubts? So suppose if you have this as s square minus 1, okay, 1 divided by s square minus 1, and then run this. So 1 divided by s square minus 1, you have this thing. Is the system stable?
No, sir.
Yes, sir. It is in middle.
Okay.
It is neither in the region of stability or else or instability.
Yeah. Just a second. Okay. So if you see here, the system is actually unstable. Okay. Why is the system unstable? You have where all you have a pole? You have a pole at 0.
Yes, sir.
You have a pole at
Not minus 1, sir.
not. You have a pole at -1, and you have a pole at 1. Okay. The transfer function was what? 1 divided by s square minus 1. So what are the roots? +1 and -1.
-1 and 1.
Yeah,
Yeah.
-1. So this is -1 and this is 1. So is the system stable?
No, sir.
Unstable. Okay. Now, so what are you trying to do? Can you make the system stable? So what do you need to do to make the system stable? Can we make the system stable with the changing the gain value? Is the system becoming stable?
Yeah.
No? The one root is always on the right side here. Okay. So whatever I do, I can't get the 2 poles on the left side. Okay. I can make it marginally stable. Okay. I can bring the 2 roots. If I go to the compensator, this is the value. Okay. For this value, the system will be marginally stable, but it will not become stable. Okay. I can't get a stable system with this. So what do I do? Can I have a PI controller?
Yes, sir.
So system is unstable. So I'm having a PI controller now. So for that, what should I do? I should have a pole at 0, correct?
Yes, sir.
Yes, sir.
Pole, the location must be 0, and then I need to have a real 0, okay, I'd say -1, okay. Now can you make this stable? No, right?
No, sir. We cannot do.
So it's just varying over here, okay. It is just varying here, it's on the right side, okay. So what I do, I go to this and delete this real 0, okay. I add a complex 0. By adding a complex 0, what am I doing? What type of controller is this?
PI controller.
Complex 0. 2 zeros.
PID, sir.
PID. Okay. It is, the equation is what? KD s square plus KPS plus KI by S. Okay. So it is 2 complex zeros. And now if I move this to the left side, the system becomes stable. Okay. Now I can move this towards the zeros, so the system becomes more. I try to get the required output. Okay, so you can vary this. Now I am in the stable region. So what we have done, we have taken a transfer function which is unstable and used a controller to make it stable. Okay, we have used a controller to make it stable. Any questions in this?
No, sir.
Okay. So, will you all be able to do the assignment? If even if you have only a mobile, so do the root locus, do the pole 0 map. Okay. If you have a laptop, then go for the control system designer, Simulink. If your internet is good, if you have installed the MATLAB in your system, then you can use Simulink easily. So try whatever is possible with these things so that you will learn better. The theory and the lab, it will help. Any questions, please ask. You just have to play with this control system designer for some time. Then you will understand what is happening. Okay. So you had two roots, you had two poles at -1 and +1, but now you have 3 poles because you added a pole, and then you have 2 zeros here. Okay. So what is the role of 0? What did you observe? What is the role of 0? Poles, we know it affects the system stability. Okay. Poles affect the system stability, but what about zeros? What about zeros? What does zeros do? If it affects the response, okay, it affects the response. How much is the overshoot, settling time, okay, rise time, all those it will affect. The zeros will affect, but it will not uh, make the system. It will not define the stability. Okay, it will not define the stability. It will define the response of the system. Any questions? See, if I move to the right, the poles, the system becomes unstable. Okay, if I move it towards the left of the zero, then the system is stable. Okay, so this is marginally stable. I'm exactly at zero, so I move to the right, it becomes unstable. Move to the left, it is stable. Any questions? What do you mean by moving to the left and moving to the right? You're changing the gain values. Okay, you're changing the gain values. So you're changing the K by moving these things. Okay, so if you right click and edit compensator, you'll get this. So this is the controller. 4.4246 into 1 plus 1s plus 0.71 s square by s. So this is the controller part, GC of s. Okay. Any questions?
Sir, what happens for the system when it is in a marginally stable state?
What happens to the system?
Yeah, sir.
Yeah. What happens to the system is the system just oscillates. Okay. Suppose you are driving a vehicle and you have a speedometer. Okay. So if that speedometer, suppose you are going at 40 kilometer per hour. Okay. And that speedometer needle doesn't stop at 40 but vibrates between 38 and 42 continuously.
Yes, sir.
That is marginally stable. Did you understand that example?
Yes, sir. Right.
Means the system is continuously oscillating. The value is changing but not changing very much. Okay, it's between that range. That is called as marginally stable. You are not getting some 1000 or 2000. You are between 38 and 42, but you needed 40. Okay.
Okay, sir.